Hello, everyone. I'm Shannon, and I'm here with my colleagues, Shri, Devin, and Michael. Today, we are discussing our project, Flood Detection using Spacenet dataset. For those of you that aren't familiar, Spacenet hosts seasonal competitions open to anyone to partake in. This is their 8th competition. Lately, deep learning has become more involved in flood detection. It shows promise of fast detection that doesn't require complicated infrastructure to be in place, such as flood sensors. We can simply use satellite or UAVs like drones to capture real-time shots and determine if there is flooding present. The dataset we are working with was provided by Spacenet, and actually 2 of our colleagues already presented their work of it in this class. So I'll quickly go through a refresher of key points and provide brief context for our project so we can get to the good stuff. The dataset is made up of 3 geographical areas, 2 known locations, and 1 unknown location, later to be revealed once the competition closes. There are also 2 broad goals for models to learn: segmenting roads and buildings without any flooding present, as well as detecting the speed of the roadways, and then detecting the presence of flooding. You may now recall that this baseline model is composed of 2 separate models, each handling one of these main goals. The foundational features network is a UNet-style segmentation model with a ResNet34 encoder. This is responsible for segmentation. The flood attribution network is a Siamese convolutional neural network, which is composed of 2 identical branches with shared weights and enables feature extraction from pre- and post-flood image pairs. This model detects presence of flood. This is accompanied as well with just some post-processing to convert the raster data to vector data. Our overall goal here in this project is either to increase accuracy or increase the speeds of the models. We looked at 2 methods to replace the base model with, the HR former and the attention UNet.
So the first model that we will be describing today is known as the HR former architecture, which was proposed in 2021. The successor to this architecture, or the predecessor rather, was known as HRNet, and was actually the winning architecture on the Spacenet 7 database. So it makes a lot of sense to employ the next generation model on the next generation dataset. This architecture is an extension of a transformer model and uses a self-attention mechanism to describe the local features found in a given image. It also employs a hierarchy structure to allow the model to capture both global and local context of the given image. We can see here that there is, in a single unit, both the self-attention layer and the depth-wise convolution, which allows features to be extracted from the local variables described by self-attention. We can see that by interlacing all of these units in succession and by computing in parallel both global and local features, that we are able to achieve a very high quality image segmentation that is a lot more complex, but a lot richer of representation compared to a standard unit model, which doesn't compose a global feature the entire time. We can see that by calculating in parallel both the global and local features, and by keeping a high and low dimensional latent space, that we're able to create a lot richer of a representation for the image. So a downside of this is that it takes a lot longer to train, given that there's a lot more going on in this model, but the work that we're putting in is rewarded with a better representation of the image, and as a consequence of that, better results on image segmentation, which we've seen in other results of this paper and of this architecture.
Talking about the attention unit. The attention unit in the context of image segmentation is a way to highlight only the relevant activations during training. It borrowed the idea of an attention mechanism from NLP and used it in skip connections. It gave the skip connections an extra idea of which region to focus on while segmenting the given object. This works great even with very small objects due to attention present in the skip connections. It reduces the computational resources invested on irrelevant activations and provides better generalization of the network. As you can see in the picture, a block diagram of the proposed attention net segmentation model. Input image is progressively filtered and downsampled by a factor of 2 at each scale in the encoding part of the network, which is present on the left side, where for example, H4 equals to H1 by 8. Here, NC denotes the number of classes. Attention gates, which are edges, filter the feature propagated to skip connections. Feature selectivity in attention gates is achieved by use of contextual information, which is also called as gating, extracted in the coercer scales. Further talking about the expansion of attention gate, as you can see in the figure, attention unit takes two inputs, vector x and g. The vector g is taken from the next lowest layer of the network. The vector has smaller dimensions and better feature representation given that g comes from deeper network. Here in the figure, vector x would have the dimensions of 64 cross 64 cross 64, which means filters cross height cross width, and vector g would be 32 cross 32 cross 32. Vector x goes through a sided convolution such that its dimensions become 64 cross 32 cross 32, and vector g goes through 1 cross 1 convolution such that its dimensions become 64 cross 32 cross 32. The two vectors are summed element-wise. The process results in aligned weights becoming layer while unaligned weights becoming relatively smaller. The resultant vector goes through a railway activation layer, as you can see, and a 1 cross 1 convolution that collapses the dimensions to 1 cross 32 cross 32. This vector goes through sigmoid layer, which scales the vector between the range 0 to 1, producing the attention coefficient, which are weights, where coefficients close to 1 indicate more relevant features which are expected. The attention coefficients are unsampled to the original dimension 64 cross 64 of the vector using trilinear interpolation. The attention coefficients are multiplied element-wise to the original x vector, scaling the vector according to relevance. This when passed along in the skip connections as well. Further, as you can see here in the picture, which is taken from the paper called Attention Unit Learning Where to Look for the Pancreas, this diagram contains a picture at 3, 6, 10, 60, and 150 epochs. As number of epochs go by, the weights of attention is more and more focused towards interest region. That's what we are trying to achieve here.
So we set up our experiments using Docker. We deployed 3 different models: the base model we're testing against, a high-resolution transformer implementation, and an attention unit implementation. We also utilized Google Cloud to take advantage of GPU computing. And then we compared the models for speed and accuracy against the base model. So we're still training and working on our final results, but here are some expected results. For the HR former, we expect higher accuracy because it maintains high resolution representations. This is important for satellite imaging, which tend to have lower resolution and harder to distinguish features. We also expect comparative training speeds because it can be trained in parallel. Below, you can see some results from the Yuan et al. Paper, looking at a standard CNN network versus their HR former model. You can see similar number of floating point operations, but higher accuracy across different segmentation benchmark data sets. For the attention unit, we also expect higher accuracy than the baseline model, but a slightly slower inference time. You can see here results from the Octave paper on segmentation for different organs. The attention unit performs just as good or better than the standard unit, and only a slightly slower inference time. So some next steps would be experimenting with other architectures, such as graph UNets or graph convolution networks. Expanding the data set to include additional regions could also improve accuracy, possibly done by incorporating UAV imaging into the data set as well. And then optimization of the loss function and hyperparameters could also improve accuracy. Here are references, and thank you.